Recurrent neural networks have diverse application in many sequence-centric settings. The applications of recurrent neural networks extend to image captioning, speech recognition, handwriting recognition, protein recognition, and machine translation. In this video, we will discuss a few of these applications as well as the specific changes that need to be made to recurrent neural network architectures and methodologies in order to enable these techniques. As we discussed in the previous video, there are many small variations to the basic architecture used in neural networks. The architecture that you see on the top left is the most basic type of neural architecture in which there are no missing inputs or outputs. This type of architecture is used in applications like forecasting and language modeling. However, in many applications, there might be missing inputs or outputs. One example of a case where you have missing inputs, which is shown on the upper right, is that of image captioning. In image captioning, you have a single input at the first timestamp corresponding to the neural representation of an image, and the outputs at the various timestamps correspond to the words associated with the caption. Note that the length of the caption may be variable length. In the case of sentiment analysis, which is shown on the lower left, you might have a sequence which is typically a sentence, and you might want to predict the sentiment of that sentence, whether it's positive or negative. So again, in this case, you might have variable length sequential inputs, but you have a single output at the very end when you're trying to predict the label of the sentence. Finally, you might have cases where there are both missing inputs and outputs. An example of this is machine translation, where the initial part, which is a sentence in one language, might have missing outputs, where the second part, which outputs the sentence in the other language, might have missing inputs. Note, however, that in machine translation, we are actually putting two recurrent neural networks together. Now, in all of these applications that we are going to discuss, we are going to use a simple example of a vanilla recurrent network. In reality, most of these applications, they are enabled by advanced variations of recurrent networks, such as, for example, LSTMs, GRUs, or multi-layer networks. So let us now talk about the issue of missing inputs. As you saw in the previous slide, many applications might have either missing inputs or missing outputs. Missing inputs generally represent a bigger challenge than missing outputs. And these missing inputs often occur at inference when the output is itself a sequence. And examples of these types of applications include language modeling, image captioning, and machine translation. The problem in this case is that when you're trying to predict an output containing multiple words, such as, for example, a caption, how does one output the second word in the caption without knowing what the first word is? So simply setting the missing inputs to either a 0 or to some random value will result in bias. So in order to handle this goal, the missing inputs are often sequentially sampled from the outputs at the previous timestamp at inference time. And this will be discussed a few slides later. Now, one observation is that we are going to present these applications assuming a simple recurrent neural network, even though in reality, all of these architectures, they are typically enabled using advanced variants. And however, the principles, these basic principles are generalized to any type of architecture. So let's first talk about language modeling. In language modeling, you're trying to predict the next word given the beginning part of a sentence. Now, this type of approach can also be used for time series prediction. So, for example, in time series prediction, you would have a part of the time series and then you're trying to predict the next element of a time series. So the only difference between a time series and let's say language modeling, we're trying to predict the next word, is that in the case of a time series, your elements of the series are real valued. Here your elements of your series are discrete. So let's look at the sentence over here, which is the cat chased the mouse, and let's assume for now, for simplicity, that you always want to predict the next word given the previous word. So for example, if I give you the cat, you want to predict the. So here I've shown, so you want to predict chase. So if I give you the cat, you should be able to predict chase. So as you can see, each timestamp, each time layer has both an input and an output. So for example, at the first timestamp, the input is the, and it's the one-hot encoded representation of the. So here you have a dictionary containing only four words, and the is the first word in the dictionary. So you can see the one-hot encoded input is 10000, and then you have a hidden layer containing just dimensionality of 2. And then you have an output which has the same dimensionality as the input because you have a vocabulary of 4, so it will have 4 elements and you will have 4 scores corresponding to how likely it is that each of the word occurs. So you can see you have score of the, score of cat, score of chase, and score of mouse. Now in most cases, in practical application, you will actually apply a softmax on top of this. Here I have not applied a softmax, so you're just multiplying the hidden state with WHY to get a real valued score. And similarly, at the next word, it's a similar model where you enter cat, and again you're trying to predict chase. Now, as you can see on the first word, actually it predicts it incorrectly because it gives mouse a score of 1.7, whereas it gives cat a score of 1.3. But as the sentence goes on, the accuracy improves because it has more context. As it has more context, so for example, the cat chased the, so then it becomes more likely that it's going to be mouse. So this is how language modeling applications work, because they have already been trained on similar sentences in order to expect what is the next token. And this broader approach can be used for any kind of prediction element, such as predicting the next element in any kind of time series, any kind of sequence. It can even be used for outlier detection. So for example, if what you observe, if a position that you observe is very different from the position that you predict, then that position is most likely an outlier. Now this basic principle of language modeling, you can use it to generate a language sample. The way you can use it to generate, here you are assuming that you always have a segment of a sentence available in order to predict the next word. However, in generating a language sample, what happens is that you have the problem of missing input, because here when you're predicting a next word is straightforward because all inputs are available. You have the segment of the sentence already available for which you're trying to predict the next word. Now, when you have missing inputs, what you do, and this approach, by the way, we use it in all applications involving missing inputs. That's true for image captioning, that is true for example, machine translation. So what you do is that you sample, so when you have output, so for example here, when you have a set of outputs for cat, you have a set of scores. You can convert these into probabilities using a softmax. Now you sample one of the words using softmax, using that probability, and you input it to the next timestamp. Now, of course, when you do this type of sampling, you may not sample accurately. So, for example, there will be a non-zero probability that you will sample the, which is going to make your prediction is even harder, because then you'll have 2 the's, and the model won't know how to predict the next word. So the way in which you handle this problem is that to improve accuracy, you have to try many possibilities. So what you do is that you use a beam search to expand on the most likely by always keeping track of the best sequence prefixes of any particular length. So for example, when you're processing the third position, and let's say B is 10, so you keep the 10 best sequence prefixes which have the highest probability, and then you try to predict the next word, and then for the next word you again predict the highest probability word over all of these possibilities, and by doing this you can generate an arbitrary sequence of text that reflects the training data set. This type of approach, and this type of approach actually has been used by a character level recurrent neural network. Now this character level recurrent neural network was implemented by Karpathy, Johnson and Feifei, and the code of this is also, the authors have made it publicly available. So when this network was executed for 5 iterations, and then a language sample was generated using the beam search approach discussed in the previous section, what happens is that you get a language model which looks something like what is shown on the slide here. Now you can see that there are a lot of spelling mistakes, and the grammar is also quite incorrect. Now some of the spellings are correct, like for example, laughter is correct. So clearly it's learning something, but there's a lot of gibberish too. The other thing that you can see it's learning the indentation quite well. So you can see that it always gets, because these are William Shakespeare's plays. So it's learning that when a character speaks, always that person is capitalized, and then you put a colon after it, then you move on to the next line to get to the verse. Now, this is because we trained it only for 5 iterations. So in 5 iterations, you actually do quite poorly. Now, suppose you were to increase this. Suppose you were to increase it to 50 iterations. Now, you can already see that there are a lot fewer errors, lot fewer spelling mistakes, but there are still some spelling mistakes. In fact, the authors, they have made some samples of their outputs publicly available. So, and in the book I have given pointers to that. You can also Google it. You can see they're quite impressive samples. Now, of course, these samples are gibberish. They don't really mean anything. They don't really truly reflect Shakespeare's plays, but nevertheless, they roughly reflect the syntax as well as the indentation of Shakespeare's plays. So one question, of course, arises, what's the use of generating this type of language sample? It may seem like an exercise in futility because the samples are syntactically correct but not semantically meaningful. It turns out that this type of language modeling is actually very useful. It's particularly useful when you condition it on some other data. So for example, you can condition it on another image. So that is the problem of image captioning. Or you can condition it on a sequence. So when you condition it on a sequence, that is what you call machine translation or sequence to sequence learning. So in all of these cases, what happens is that because you start off with a conditioning, it will give you a syntactically correct sequence of words, which is very reflective of that particular element that you condition it on. So you will get very meaningful output. So let's look at one example. For example, image captioning. So in image captioning, what you do is that you train it over image caption pairs. So your training data contains pairs of images and captions. And what you do is that you hook up a recurrent neural network with a convolutional neural networks. And it's important to train both of the two networks together. So what you do is that for your pairs of images and captions, you continually train both the convolutional neural network and the recurrent neural network together. And here you will note that I have a start and end token too. At each word, I have a start and end token. So in this case, the caption of the image is Cosmic Winter Wonderland. And you to start off the caption, even in the training data, you put a start token, so that outputs the first token, which is cosmic. And then whatever token you get, you input it to the next timestamp to get winter. Now again, you are going to have to use beam search, the approach that I discussed in the previous slide for missing inputs. Because note that this is also a case with missing inputs, and the inputs are really being inherited by the outputs on the next timestamp. So you're always going to have to keep the prefixes at inference time. You're going to have to keep the prefixes of the captions and keep the top B prefixes and keep inputting to the next timestamp in order to learn the best sentence. And this type of image captioning approach, it has actually been used very successfully in order to provide meaningful descriptions of images. The next example is that of sequence to sequence learning. So here your input is a sequence and your output is a sequence. Now note that the most basic application of sequence to sequence learning might be just that of copying one sentence to itself. That's basically a recurrent autoencoder. Here there is a slight difference from the recurrent autoencoder, because here what I have done is that you have two different recurrent networks which are hooked end to end. So the parameters in RNN1 and RNN2, they are not shared. They are different sets of parameters. However, if you had a recurrent autoencoder, presumably you could do it using the same set of parameters across the whole recurrent network. But in any case, even that is not necessary. With an autoencoder also, you could have different parameters. You could have two recurrent networks hooked to end to end, even in the recurrent, even if your application was that of copying one sentence identically. But here, let's just look at machine translation, because that is the most important application of sequence to sequence learning. In fact, the Google Translate output that you see, my understanding is that it currently uses this type of neural network based machine translation. So here you can see that the first part, RNN1, it has missing outputs. So here the inputs are I don't understand Spanish, and then then we move on to the next recurrent network. It's hooked on, and the next recurrent network, it is joined to the by using the weight WES. Now note that this weight WES would be needed if the hidden layer dimensionality of the second recurrent neural network is different from the first. However, if the hidden layer dimension is not different, you can just set it to some constant value such as 1. And now here you can see you have two sets of parameters and you train them end to end. So you will have your training data will contain pairs of sentences in English and sentences in Spanish, and you will train both the recurrent neural networks end to end, and then at inference time you will only input the English sentence, and of course you will have missing inputs. There's the same problem of missing inputs when it comes to the Spanish sentence, but what you will do is that when you output the first word, you are going to input it to the next timestamp, and you're going to try various possibilities, again using beam search, in order to find out the best sequence that matches the particular English sentence, which has the highest probability. That best sequence using beam search, you do that using the highest probability. Then another application, of course, is sentence level classification. In fact, this application is what we started with when we introduced recurrent neural networks. So here you can see that you have a sentence, and then when you input the tag corresponding to end of sentence, that's a cue to the recurrent network to output the label. So again, your training data will contain these types of sentences together with a tag as well as the output of the sentiment, and after training it over many such training pairs, is going to learn how the sequence in the sentence affects the sentiment. Now note that the ordering of the words matters when you're talking about an application like sentiment analysis. So for example, if you had a sentence like I love this iPod and I hardly love this iPod, they have totally different sentiments. So you can see clearly that in both the two cases, your recurrent neural network, because it's sensitive to the sequence, it will be able to learn that this particular word occurring at that position changes the sentiment. And that is why recurrent neural networks are able to do very good sentiment analysis, whereas it is hard to do this using a bag of words approach, because it's unable to use the sequential ordering of the words to make predictions. And then in some applications, you have token level classification, where for each word in the sentence, you have a class label. So here, for example, this occurs often in applications, for example, such as information extraction. So here you have a sentence, William Jefferson Clinton lives in New York. So William Jefferson Clinton, these are tokens representing person, then lives is other, token of type other, in is a token of type other, and then new is a token type location, and York is a token type location. Now here I've also added some additional input corresponding to linguistic features. So these applications, they do provide you the flexibility to add other types of inputs corresponding to various linguistic features, such as the part of speech. So if you have other additional information, you can add that to the input. And then again, this is going to output the label for each token. This is actually quite a simple application. Because this doesn't have any missing inputs or any missing outputs. Then you have temporal recommender system. So imagine you have a case where a person is browsing the internet. So they have web access, their contents, or they are browsing items at a shopping site, and you want to predict what's the next item they will browse. Or you have a set of items that they are going to buy, a sequence of items, and you want to predict what's the next item they are going to buy. So this kind of algorithm, it uses a combination of a recurrent network as well as some static networks. The reason you need some static networks is because you also have some static information about the item which is being browsed, as well as, for example, the description of the item, and you also have some information of the user. So, for example, you may have some information of the user, like what is the user's profile, what are the user's interests, what kinds of things the user likes. The user may have entered that at the site. So at the same time, the dynamic information, what the user has, that this window of accesses, that also has an effect on what the user is going to browse next. So in order to handle that sequence of access, you use a recurrent neural network, and you fuse the recurrent neural network hidden state embedding with the embedding of the user's profile, and you will get a fused user embedding at time t, and then you will have the item embedding. So that way you can use these two to get a rating value. Now this rating value might simply be a implicit feedback rating. That means whether or not the user is going to access at time t. Then we have another application, which is protein structures prediction. Now note that the elements of the sequence are symbols representing one of the 20 amino acids, and the 20 possible amino acids, they are akin to the vocabulary used in the text setting. And in this protein structure prediction, each position is associated with a class label. For example, like alpha helix, beta sheet, coil. And this problem is very straightforward, because here you have there are no missing inputs or outputs. So you can reduce this problem to token level classification. There are some other applications also for speech and handwriting recognition. So in speech, frame representation of audios is transcribed into character sequence, and in handwriting, you convert a sequence of strokes into a character sequence, and the details and references of these applications are given in the book.